convection. Right, this is another form in which heat can travel, and this method is used in liquids and gases. Okay, you need to explain it in terms of particles. And the first thing to know is that it's to do with whenever you put energy into a system, you cause the particles there to move around faster, and they therefore take up more space. You can see the cool gas is a small area, hot gas is the particles moving faster and they've spread out. You can see there it says particles faster, they're further apart. The gas expands, that's a good word to use in the thing. The gas expands and it becomes less dense. Now, make sure you know that less dense does not mean it's less heavy. Less dense means it's less heavy for its size. And perhaps the best analogy or comparison I can use is what weighs more, a ton of lead or a ton of feathers. Well, of course, they both weigh the same, both of the same mass, but of course the feathers take up a lot more space. And that's what happens with liquids and gases. When you heat them up, they take up more space. So you can see a ton of cold air has less volume than a ton of hot air. And this property of gases and fluids expanding is how heat travels through them. If we look at this diagram here, this is supposed to represent someone's house, for example, on a sofa, and there's a radiator by the wall, and you have cold air next to the radiator. Now the radiator then heats up the air expands. So if you notice, box 1 has become box 2, which is much bigger, and because it's a much bigger box, its density is less, and so therefore it floats up to the top of the room. At the top of the room, it travels across from 3 to 4, and then it begins to cool down a little bit. And as it cools down, the gas contracts, it sinks down to 5. And of course, because air has gone from where 1 is and where 2 is, there is a bit of a vacuum there, and that sucks in the cool air. So sooner or later, all the air gets warmed up. But if you measured the temperature of the air at the top of the room, it is always warmer than the air at the bottom of the room. But that's how heat travels in liquids and gases. Sometimes the examiner may talk about another example. A popular one is something like a freezer. If we start in the top left-hand corner here, that's where you tend to find an icebox, or in the top of the fridge. And what the icebox does is it cools down the air, so the air contracts, it becomes more dense, it sinks down towards the bottom, and of course as it sinks down towards the bottom it creates a bit of a vacuum at the top, and other air rushes in to take its place. The air is pushed around by the fact that one part of it is getting dense and it sinks and it causes the air to move around. And that's how a fridge keeps cool. It keeps cooling down any warm air in there. You may find in the exams they may try to present convection in the form of sea currents. So, for example, there's a very famous current called the North Atlantic Drift, which works on convection, the same sort of process. It may be based on balloons, about how a balloon works. When you heat the air inside the balloon, the gas expands, becomes less dense, and rises. Boiling water. All the winds of the world are created by convection. And fires, for example. So if you look at the equator of the Earth, there's a lot of heat energy. The air above that expands, it rises to the top, and it sets up as a convection current, similar like the one you see on the Earth there. And the Earth has got loads of little convection currents like that, and that drives the world's weather. So there you go. That is convection, and we finished for the session.